this is wrong, or this is a huge discovery. And we think that it's a huge discovery.
Far beyond the reaches of our galaxy, the James Webb Space Telescope has been capturing breathtaking images and uncovering mysteries hidden in the depths of the universe. But now, one of its latest discoveries has left astronomers baffled, and a Nobel winner has stepped forward with a chilling warning. What exactly has Webb found out there in the darkness? The answers might be more scary than we're ready for. The vast universe. Our universe is often thought of as the grandest arena imaginable, a boundless expanse filled with stars, galaxies, and many unknown wonders. Astronomers define the universe as the totality of everything that exists, including all matter, energy, and the physical laws that govern them. While this sounds simple on the surface, each new observation reveals complexities that continue to amaze scientists. For much of human history, our place in the cosmos seemed limited to what we could see with our eyes. Then came economic and scientific advancements that produced telescopes, satellites, and other tools capable of pushing our view deeper into space. Today, we know that the Earth orbits a typical star we call the Sun, which lies in a spiral galaxy named the Milky Way. Beyond our own galaxy, there are countless others, each teeming with billions or even trillions of stars. Yet even calling these numbers countless hardly captures the scale. The observable universe, which is the portion we can see due to the finite speed of light, spans about 92 billion light-years across in diameter, numbers that tend to boggle the mind. And that 92 billion light-years is only the limit of what our instruments can view. The universe likely extends beyond that horizon. One deep concept in cosmology is that looking at distant objects is akin to peering back in time. Because light takes a set amount of time to travel, a galaxy seen as it was 10 billion years ago offers a snapshot of the past. This time travel quality is key to understanding how things like stars and galaxies formed. By observing a wide range of distances, astronomers piece together an approximate timeline of cosmic events. They look for the faintest signs of the earliest stars and galaxies to discover what conditions prevailed shortly after the universe's beginning. The Big Bang theory, which has guided cosmological thinking for decades, provides a framework for how the universe might have started around 13.8 billion years ago in a hot, dense state. The theory says that space itself expanded, spreading out matter and radiation. As the hot, dense soup cooled, particles combined to form atoms. Later, gravitational pulls helped assemble these atoms into the stars and galaxies we see today. However, emerging observations from new telescopes sometimes disagree with what models predict. Even something as fundamental as the universe's age can feel uncertain when data implies that galaxies were already well established at times a standard model would consider too early. Modern telescopes, such as the James Webb Space Telescope, JWST, are redefining our sense of cosmic time by showing astronomical structures that appear more mature than expected when the universe was still in its proverbial infancy. Researchers pore over these results to compare them with existing cosmological models, such as the standard lambda-CDM model, which incorporates dark energy, lambda, and cold, dark matter, CDM. If observations deviate too far from predictions, major revisions to that model might be necessary. This possibility stimulates debates among astrophysicists about dark energy, dark matter, the rate of expansion, inflation, and how everything fits together. At the same time, scientists must factor in how cosmic distances and the physics of light can affect what we see. Natural limitations, like our inability to detect objects dimmer than a certain threshold, complicate efforts to verify or dismiss theories easily. Yet, our perseverance in refining technology and building knowledge is rooted in curiosity. We want to know not just how the cosmos looks, but why it looks this way, whether it's truly isotropic, and if the story of the Big Bang is complete or needs rewriting. Telescopes and the light they capture. We uncover cosmic secrets primarily by catching light. Telescopes are meticulous light-collecting machines that help us analyze everything from nearby asteroids to the edges of the observable universe. The idea of a telescope is straightforward: gather more light than the human eye can handle and magnify it. But the technology behind modern telescopes is anything but simple. There are multiple categories depending on the wavelength of interest, such as optical, radio, infrared, ultraviolet, X-ray, and gamma-ray telescopes. Each reveals a specific slice of the universe's story. Historically, Galileo's early telescope showed humans that Jupiter had moons and that Venus had phases, sparking the realization that Earth is not the universe's center. Centuries later, large ground-based telescopes like the Keck Observatory in Hawaii or the Very Large Telescope in Chile use mirrors that measure many meters across, collecting huge amounts of light. Earth-based telescopes, however, face problems like atmospheric distortion and light pollution. Adaptive optics can correct some of it, but many astronomers dreamt of telescopes in space, where the atmosphere wouldn't blur images or absorb key wavelengths. The Hubble Space Telescope, launched in 1990, revolutionized our entire view of cosmic history. By operating above Earth's atmosphere, Hubble captured some of the most iconic images in modern astronomy. Its deep-field observations showed thousands of galaxies in what once seemed like an empty patch of sky. Hubble also helped refine the Hubble constant, the rate of cosmic expansion, and mapped out star-forming regions in exquisite detail. Yet, it mostly used optical and ultraviolet instruments, which only partially told the cosmic story. Infrared astronomy became crucial for looking deeper into the universe. Because of cosmic expansion, light from extremely distant objects gets stretched, redshifted toward longer wavelengths. By shifting from ultraviolet and visible to infrared, older galaxies can ironically appear bright in the infrared region. The James Webb Space Telescope, JWST, therefore, filled a pressing need. Its large, segmented mirror, advanced infrared sensors, and position at the second Lagrange point, L2, make it sensitive enough to collect photons from objects formed a few 100 million years after the Big Bang, a time that was previously only faintly accessible. The James Webb Space Telescope in practice. JWST stands out because it was specifically designed to probe the universe's earliest epochs. Its massive mirror, about 6.5 meters across, and unique cooling system allow it to detect faint infrared signals. The sun shield, composed of multiple layers, keeps the instruments extremely cold, preventing interference from the telescope's own heat. Once it arrived at L2, JWST underwent a complex unfolding sequence, aligning each mirror segment so that they functioned as one. Space fans worldwide watched with bated breath for the first images to come in, and they didn't disappoint. One particularly famous early release was JWST's deep field image, taken using its near-infrared camera, NIRCam. This snapshot unveiled thousands of galaxies, many so distant that their shapes were warped by gravitational lensing. Scientists saw arcs, swirls, and fuzzy spots that might correspond to baby galaxies from the earliest billion years of cosmic history. For them, each little blob is a clue that either confirms or questions what we know about how matter coalesced into galaxies. Spectroscopic data from JWST's NIR-SPEC near-infrared spectrograph and MIRI mid-infrared instrument promise additional revelations: the chemical makeup, star formation rates, and velocities. An important part of JWST's mission is to zoom in on targets that earlier telescopes flagged as interesting. For example, if Hubble discovered a galaxy that appeared unusually red and bright, JWST can take a closer look, decipher the lines in its spectrum, and estimate how far away it is and how fast it's forming stars. Some of JWST's best-known findings involve galaxies like JADE's GSZ-14, proposed to exist roughly 290 million years after the Big Bang. That figure alone warrants intense scrutiny. How do you get such a bright, massive system in such a short window of cosmic time? Astronomers also found galaxies that seem to have turned nearly all of their available gas into stars, rather than the usual small percentage. This is baffling because star formation is typically limited by factors like feedback from supernovae and the availability of cold gas. If JWST keeps spotting these overachieving galaxies, the rules of star formation that astronomers have used for decades might need serious adjustments. The tension between observation and standard theory is not a minor detail. It cuts to the core of how matter behaves under gravitational forces in the universe's first eras. The challenge to the Big Bang timeline. The classic timeline of the Big Bang describes how the universe went from a scorching, dense point to the cooler cosmos we see today. In the earliest moments, energy levels were incredibly high. The fundamental forces acted differently, and particles combined and broke apart in ways that are difficult to imagine. As expansion continued, the cosmic microwave background, CMB, was emitted around 380,000 years later, when neutral atoms formed and light finally traveled freely. After millions more years, matter began gathering into the first stars and galaxies. Yet, JWST's observations suggest that well-developed galaxies appeared earlier than standard outlines predict. If the cosmos is about 13.8 billion years old, you might expect the earliest substantial galaxies to show up maybe 500 million to a billion years after the Big Bang. But some targets identified by JWST appear to be less than 400 million years post-Big Bang, and they don't look like tiny infant galaxies. Instead, they're bright, with many stars, and seemingly well-structured. A few of them defy the normal ratios of gas to stellar mass, as if cosmic processes acted very differently than we'd expect in those times. The discrepancy has led some scientists to propose that the universe could be older. Others suggest that the early formation of galaxies was more efficient than models allow. Perhaps there are processes that can accelerate star formation, like extremely dense gas pockets or faster cooling rates. Another angle is that some ancient black holes, known as quasars, might masquerade in data as big, bright galaxies. If that's the case, the puzzle might not be as big a threat to the standard model, though it still demands explanations for how supermassive black holes appeared so fast. It's also possible that our distance calculations need refining. Techniques like redshift measurements are generally accurate, but certain dust conditions or unusual emission lines can mimic large cosmic distances. Astronomers double-check results by comparing different measurement methods. If the super-early galaxies are confirmed as truly that old and big, the community can't ignore the fundamental friction with accepted theory. This is largely why data from JWST started so many discussions, both professional and public, about whether the standard Big Bang narrative is complete or if it must be stretched, bent, or replaced by something new. Dark matter and dark energy revisited. Dark matter and dark energy are pivotal elements in the lambda CDM model. Cold dark matter, CDM, helps explain how galaxies and galaxy clusters keep their shapes, given that the gravitational pull from visible matter alone isn't enough. Dark energy, lambda, is associated with the accelerated expansion that perplexed astronomers in the late 1990s. While the ratio in the standard model, claims around 68% dark energy, 27% dark matter, and only about 5% ordinary matter, we haven't directly detected dark matter or dark energy in terrestrial experiments. JWST's surprising galaxy observations raise questions about structure formation and mass distribution. The conventional assumption is that dark matter clumps first, creating gravitational wells into which normal matter fall, igniting star formation. If we see massive galaxies too soon, is it because dark matter scaffolds formed somehow faster, or is there a shortfall in that assumption? Some propose new types of dark matter, warm or self-interacting forms that might condense or cluster at different rates. Dark energy similarly faces scrutiny. The acceleration of the universe's expansion was originally documented using Type Ia supernova observations, something that earned teams like Adam Riess's group a Nobel Prize. These supernovae served as standard candles, meaning their luminosity was predictable enough to gauge distance. The data implied that expansion didn't just continue, but sped up over time. If the early universe's structure formation is different than predicted, some wonder whether dark energy's effect might have varied across time, or if an entirely different mechanism altogether is at play. Modified gravity theories, such as MOND, modified Newtonian dynamics, and others, often are touted as alternatives to the concept of dark matter. However, they have difficulty providing a strong substitute for dark energy. Some extended or hybrid theories aim to handle both in one framework. Still, no single alternative has swept away the standard model because it usually fails to address all observational constraints, like the patterns in the cosmic microwave background or the distribution of galaxies. Early star formation. Star formation is usually envisioned as clouds of gas and dust collapsing under gravity until nuclear fusion ignites in a newly formed star. The rate of this process depends on numerous factors, from local turbulence to metallicity conditions, the abundance of elements heavier than hydrogen and helium. A typical statement in modern astrophysics is that most galaxies can't efficiently convert all their gas into stars because various feedback mechanisms like radiation pressure from stars, stellar winds, and supernova explosions blow a lot of gas outward before it can form more stars. This paradigm has guided the development of galaxy evolution theories. Computer simulations that model how dark matter halos gather normal matter also incorporate star formation laws that appear fairly consistent with observed galaxies in the nearby universe. But if JWST is detecting galaxies in the early universe that have turned almost 100% of their available gas into stars, it shakes that standard approach. If the usual feedback processes did not restrain star formation, we must ask what conditions allowed such runaway efficiency. One hypothesis might be that the gas in the early universe was far denser and cooler, enabling gravitational collapse to happen more rapidly with fewer checks and balances. Another idea is that some early galaxies might have been extremely compact, making it easier to retain material. Additionally, there could be unusual radiation backgrounds or hidden forms of partial reionization that changed how readily gas collapsed at certain epochs. Scientists are also mindful that some so-called galaxies might really be something else. You can imagine a scenario where an active galactic nucleus, AGN, or quasar, brightens a region so that it appears to be a fully loaded, star-rich galaxy. That's why spectroscopic follow-up is so essential. Spectra can detect specific chemical emission lines or broad signatures that arise from matter swirling around a supermassive black hole, different from a population of normal stars. Either way, it's a thrilling area of exploration. If these objects are proven to be star-packed galaxies, then astrophysics textbooks will need serious updates. If they are active galactic nuclei masquerading as ultra-early galaxies, we will have discovered more about how black holes form and feed in the universe's infancy. Both outcomes add pieces to a puzzle that's far from complete. the Hubble tension and its broader impact. The Hubble tension refers to the discrepancy in the measured value of the Hubble constant, h0, an indication of how fast the universe expands. Observations of supernovae in relatively nearby galaxies consistently give a higher expansion rate in the 73 to 75 kilometers per second per megaparsec range than observations of the cosmic microwave background from missions like Planck, which yield 67 to 69 kilometers per second per megaparsec. Both sets of measurements have become more precise over time, yet the gap hasn't closed. This difference isn't trivially small. It's a real conflict if each side's data is genuinely accurate. Adam Rees, Saul Perlmutter, and Brian Schmidt, who uncovered the acceleration of the universe, helped to refine these supernova measurements. Meanwhile, the Planck satellite gathered remarkable detail about the CMB, shaping the standard cosmological model. Explaining why these measurement methods yield diverging results is challenging. One possibility is that there's new physics at play. Another is that local calibrations or assumptions about the universe's early conditions are off. The Hubble tension might connect indirectly with JWST's surprising findings. If galaxies formed faster in the early universe than expected, that could shift certain parameters about structure formation, which in turn might influence cosmic distances or expansion interpretations. However, it's an intricate web. Many astronomers remain cautious, wanting more data to see if these early galaxy detections hold up under deeper scrutiny and if they truly deviate from the standard timeline in ways that matter for Hubble measurements. Regardless, contested results often help science progress. New missions, like the Nancy Grace Roman Space Telescope and ESA's Euclid, aim to measure large numbers of galaxies and their distances. These data could either confirm the tension or show we're missing some systematics in current approaches. If the tension persists, it could be a sign that the standard cosmological model, anchored on a certain approach to dark energy, inflation, and how matter behaves, needs reimagining. That's why many astrophysicists see the tension as a prime opportunity for breakthroughs, similar to how puzzling data in past centuries led to the acceptance of new physical law. Cosmic microwave background. The cosmic microwave background, CMB, is a relic of an era about 380,000 years after the Big Bang. Before that time, the universe was filled with charged particles that scattered photons. Once temperatures cooled enough for electrons to bind with nuclei, forming neutral atoms, photons could freely travel. That leftover radiation, now stretched into microwave wavelengths by cosmic expansion, basically comes at us from every direction. Maps of the CMB, like those from the WMAP and Planck satellites, show tiny over- and underdensities, temperature fluctuations that represent the seeds of future galaxies and voids. The standard explanation is that quantum fluctuations in the inflationary epoch, a supposed period of extremely rapid expansion, were magnified to cosmic scales, forming the patchy pattern we see in the CMB. The distribution and scale of these patches allow scientists to derive key parameters such as the matter density, baryon density, and the expansion rate. It's a remarkable feat that so many aspects of the universe can be read from a seemingly simple globe. Yet some researchers interpret anomalies in the CMB as signs of new physics or exotic phenomena like bubble collisions from a hypothetical multiverse. The cold spot, for example, is an unusually large region of lower temperature. Observations about the universe's geometry and large-scale isotropy also feed into how we interpret the CMB. If the universe is truly isotropic on large scales, that simplifies how we read the CMB data. But if isotropy breaks down, or if certain directions behave differently, the entire approach to analyzing the CMB might need rethinking. JWST doesn't measure the CMB directly, but it provides a chance to see if the early structures match what CMB-based predictions indicate. If Planck results say that cosmic structure should take a certain shape After 500 million years, we can check whether JWST sees that shape. Any discrepancies can be updated in the underlying model. Some see these comparisons as connect the dots between the extremely early universe, CMB era, and the slightly later cosmic dawn that JWST explores. If too many dots fail to match up, then we know we're missing a big piece of the puzzle, whether it's new particles, new expansions, or a different initial condition for how matter and energy were distributed. Rethinking cosmic origins. Inflation has been a staple of modern cosmology since the 1980s, proposed to solve several problems: the horizon problem, the flatness problem, and the lack of magnetic monopole. According to inflation theory, a fraction of a second after the Big Bang, the universe ballooned tremendously. Quantum fluctuations during this inflationary phase became gravitational seeds for galaxy formation. However, questions linger about what triggered inflation, what ended it, and if cosmic inflation is the only explanation. Some scientists look at new data from JWST or the Hubble tension as subtle hints that inflation might need modifications or an alternative. For example, cyclical or bounce cosmologies suggest the universe might undergo repeated expansions and contractions. Others propose varying speed of light ideas or other mechanisms that might replicate inflation's successes without requiring a separate inflation field. One bold proposal is that the universe might have no definitive beginning at all, an idea that challenges the notion of a singular Big Bang. Instead, it could be that the visible Big Bang was a transitional event in a broader cosmic framework. This interpretation arises from certain quantum gravity ideas, where classical concepts of time and space break down at extremely high energy. If JWST data shows galaxies that appear older or more developed than expected, perhaps the horizon and age constraints we once accepted are incomplete. Nobel laureates who keep an open mind, like Adam Rees and David Gross, are encouraging a re-examination of guiding cosmological principles. They emphasize that each crisis is also a chance to find deeper unity between quantum theory and cosmic-scale physics. In particular, they highlight that new phenomena might only become clear if we can gather more data about the earliest times or about the fundamental nature of matter. It's a thrilling era where the lack of easy answers might be a sign that we're on the cusp of a new theoretical unification. Quantum insights and particle time. To fully understand the earliest epochs, we must figure out how quantum mechanics shaped the newborn universe. In present-day labs, we can do particle accelerator experiments at high energy, although still vastly below the energies typical right after the Big Bang. The Large Hadron Collider, LHC, at CERN smashes protons together to see new particles or to confirm theories like the Higgs mechanism. Meanwhile, certain underground detectors look for evidence of dark matter via rare scattering events. These experiments may help link the microcosm of particle physics to the macrocosm of cosmic expansion. David Gross is one of many theorists who see the quantum realm as the key. His work on asymptotic freedom explains how quarks inside protons and neutrons behave at high energies, critical information for the early universe. Back then, we might imagine a quark soup that needed to cool before protons and neutrons could form. If something in that era changed the fundamental couplings, or if new particles existed, it might produce observational imprints we can detect in the distribution of galaxies or in the cosmic microwave background. String theory contends that what we see as particles are actually tiny vibrating strings in higher dimensional spaces. This perspective might unify gravity with quantum physics, something not accomplished by Einstein's general relativity on its own. But string theory predictions tend to be so high energy that direct testing is challenging. The early universe, however, was a natural high-energy lab. Clues about extra dimensions or string resonances might be hidden in anomalies in the CMB or in how structure forms. Even the notion of singularities, like the one the Big Bang Theory suggests, could vanish in a full quantum gravity approach. Instead, we might have bridging states or cyclical expansions that remove the need for an initial point. If JWST data, along with further CMB observations, strongly conflict with the standard timeline, more researchers might adopt quantum gravity models that permit older or repeating universes. Of course, each new layer of theory must also make testable predictions, or it remains speculative. The interplay between data and theory is essential for distinguishing valid ideas from pure guesswork. Seeing past the observable horizon. The observable universe is limited by the distance that light has traveled since the Big Bang. It's about 92 billion light-years across, but beyond that, we cannot see what lies out there. In principle, the cosmic expansion can move regions away from us faster than light, making them undetectable. This begs the question, is there an edge? Modern cosmology says that space could be infinite, meaning there's no hard boundary, just regions whose light won't ever reach us. The JWST's ability to look far out also means looking far back in time. If we see older epochs approaching the cosmic dawn, we get a sense of how structure appeared within the visible patch of the universe. But if more advanced instruments in the future push this boundary further, we might see even earlier events. Right now, the detection limits are tied to how faint these objects are. Galaxies beyond a certain redshift might be too dim for even JWST to pick up, but technology might continue to evolve. There's also the notion that the shape or geometry of the universe could turn non-trivial at extreme distances. Many standard models treat space as flat overall, with no large curvature, consistent with the CMB data, but we cannot confirm that beyond the horizon. Some also speculate about large-scale voids or bubble that might have different expansion rates or densities. Could it be that certain anomalies in local measurements reflect a larger cosmic environment that we fail to account for? The isotropy assumption is convenient, but is it fully accurate? Furthermore, the idea of a multiverse has gained traction in certain corners of theoretical physics. If inflation occurred, it might continue in other regions, spawning countless bubble universes. Collisions between these bubbles might even leave subtle marks in the CMB or in cosmic structures. However, while it's an intriguing notion, we have yet to find an unambiguous smoking gun. JWST's new data might spark renewed interest in detecting faint patterns or anomalies that standard single-universe cosmology can't explain. Thanks for watching another episode. While you are still here, make sure to click on the video on your screen for more quality content.